Hi folks, welcome to this video on kinematics with trig functions. So we've got a few things to remember here. We've done kinematics questions before, maybe even with a bit of trig, but in this video we'll sort of focus in on that. So when you see the word initially, that means that time is 0. If we see the words at rest, that means velocity is 0. If we're moving right or up or forward, that means velocity is positive. If we're moving left or down or backward, velocity is negative. If velocity and acceleration have the same signs, we're speeding up. And if velocity and acceleration have different signs, we're slowing down. We'll do two examples. And this first one says a particle moves along a horizontal line, but the particle's displacement in meters from an origin at time t is given by s of t is 4 minus 2 sine 2t. So what we need to do is find the particle's velocity and acceleration at any time t. That means we've got to find the velocity function, which is the first derivative of position. So position has a 4 out front, which turns into 0 when we differentiate. Negative 2 stays, it's a coefficient. And then we have sine turns into cosine of 2t times, because this is the sine of a glob, times the derivative. So the velocity function is going to be negative 4 cos of 2t. The acceleration function is the derivative of velocity, or the second derivative of position, or displacement. So when we differentiate this, our negative 4 will stay. We're just differentiating the velocity function. Negative 4 stays. Cosine goes to negative sine. We might think about that wheel of trig. And then we have, from the chain rule, that 2 that we multiply by. So the acceleration at any time is given by positive 8 sine of 2t. Next thing it asks us for is the initial displacement, velocity, and acceleration. So s of 0, that means we're going to go 4 minus 2 times the sine of 2 times 0. So it might be worth thinking about the unit circle here. The sine of 0 is 0. So this would just be 4 meters. It would be 4 meters to the right of the origin. Velocity at 0 would be negative 4 cos of 2 times 0. So careful here. The cosine of 0 is 1. That's negative 4 times 1, or negative 4 meters per second. And finally, the initial acceleration would be 8 times the sine of 2 times 0, which would be 0. Now we're asked to find when the particle's at rest, and then when it's moving left or right. So let's check this out. At rest means that velocity is 0. Okay? Or negative 4 cos 2t is equal to 0. And it's only on the interval from 0 to pi. And we can divide both sides by negative 4, so we get cos 2t is 0. To solve that, I would be thinking about my unit circle and saying, well, when is cosine 0? Cosine 0 at pi over 2. And it's also 0 at 3 pi over 2 in the first cycle. You might say, well, 3 pi over 2 is too big. But remember, the angle here, or the function that we're cosigning, if you want to make it a verb, is not just t, but 2t. So it would be 2t equals pi over 2, and 2t equals 3 pi over 2. In other words, it's at rest when t is pi over 4, if I divide both sides by 2. And 3 pi over 4 if I divide both sides by 2. That lets me make a little velocity diagram. So there's time is 0, that's when we start. And there's time is pi over 4. That's a really important time in the life of this particle, if we're telling its biography, because that's a moment when it's at rest. And then we go all the way up to time is pi. And I'm thinking, well, what's going to happen if I sub in a number between 0 and pi over 4 into this velocity function? Remember, the velocity function is negative 4 cos 2t. Okay. So if I were to sub in pi over 3 or something, I'm going to get a positive number for cos of 2t times a negative. So this will be negative. To start with, the velocity is negative, meaning that it is moving left. Okay? It's moving left from 0 to pi over 4. What if I were to put in a number between pi over 4 and 3 pi over 4 in for t? We could try this. You could put in, we could put in pi over 2. So you'd have negative 4 cos of 2 times pi over 2, or negative 4 cos of pi, or negative 4 cos of pi is negative 1. You get a positive velocity. In that entire region, you get positive velocities. In other words, we'd be moving to the right. So right from pi over 4 until 3 pi over 4, over that time interval. And lastly, we're going to be moving left. Velocity is going to be negative again. If you put in something between 3 pi over 4 and pi, you'll find that it works out to be negative. So these are the times and the motions over those times. And I guess we should be really clear here that it is at rest at t equals pi over 4 seconds and t equals 3 pi over 4 seconds. That's what allowed us to make that velocity diagram. Lastly, find the displacement of the particle after pi seconds. So the position or displacement is going to be s of pi. So I just go 4 minus 2 sine 2 times, in this case, pi. Okay? So that's going to be 4 minus, let's see, 2 times the sine of 2 pi. Oh, the sine of 2 pi is just 0, so we'd end up with 4, which is the same position as s at 0. So if we think about displacement as just being position, then this is what we're looking for. If we're talking about net displacement, though, that would be 0. So ideally, questions would be given a little more clearly than this. It's probably a better plan to use the word position for the actual location and to use the word net displacement when we're talking about the change in position over a certain time period. Which leaves us with a bit of an unsatisfying answer here. You can probably count on the IB to create questions that are a little clearer than this one that I just grabbed from a book. And so hopefully this sort of confusion won't be there. But net displacement would be 0 meters. The actual position after pi seconds would be 4 meters to the right of the origin. Okay, one last one. We've got a particle that moves in a straight line. The velocity function's given in this case. And in part A, they say when t equals 0, the displacement of the particle from a fixed origin is 5 meters. Find an expression for s in terms of t. So, if we were to differentiate down from s, we'd get velocity. If you want to go from velocity to position, then that means that we've got to integrate our way up. So let's write what we're going to integrate. We're going to integrate 4 sine t cos squared of t. I'm going to write that as cos t all squared dt. And some people are going to look at this integral and just be able to work it out, do it by inspection. But for the rest of us, we might at least recognize that it is a mess. And how do we deal with messy integrals? Well, we look for fancy stuff, probably look for substitution. So when I'm looking at this, I'm saying they each have a derivative to do with each other, like derivative of sine is cosine. Also, derivative of cosine is negative sine. The one that has something applied to it, or power applied to it, is cosine, though. So that's the one I'm going to make my u. And then I'll figure out du by dt. and that will be negative sine of t. And then I look and I say, oh, I don't have negative sine t. I have positive 4 sine t. So what do we have? We have negative 4 times the thing that we want. Okay? We have negative 4 times negative sine t. And that allows me to rewrite this integral. So we would have that 4 sine t is negative 4 du by dt. Sorry, that should be a dt over here. By cosine of t squared. Well, remember, cosine of t we're just calling u. Or in other words, we have the integral of negative 4 u squared dt. And that is something that is not that difficult to integrate. It's going to be negative 4 stays, power goes up by 1, flip of the new power goes in front, plus c. Now, we can't leave it in terms of u, so we're going to have to rewrite it as, instead of u, we'll put it as cos t cubed. You can call that cos cubed of t if you want. I'm going to leave it this way. So there's the function, except we haven't used all the information. The displacement from the fixed origin is 5 meters when t equals 0. Oh, so they're telling us s of 0 is 5. That may help us figure out what c is. So 5 equals negative 4/3 cosine of 0, all cubed, plus c. Or 5 equals negative 4/3. The cosine of 0 is just 1. So cubed would still be 1. And I'll keep going here. 5 is 15/3. This is negative 4/3. And this is a fairly involved problem. We have to figure out what c is. And then finally at the end we can say, all right, so the position function is negative 4/3 cos cubed of t plus 19/3. Now, if it were me at this point, I would check that. I would say, I wonder what the derivative of this is. So negative 4/3 would stay. The power of 3 would come down front. We'd have cos squared t, and then we'd have times the derivative of cos t, which would be negative sine t. And what would we get? We'd get 4 cos squared t sine t. Is that the correct velocity function? Yes, it is. That's what we started with. Whew, that was a lot of stuff. So let's keep going through the other sections. Maybe they won't all rely on each other. Find an expression for the acceleration a of the particle at time t. Okay, so this hopefully is a little bit better. In part B, we need to find acceleration, which is the first derivative of velocity. Okay. Now, that is a bit of a pain because velocity is a product. So sine t and cos t all squared. There are a bunch of ways you can think this through, but if it were me, I would go with u is 4 sine t. And feel free at any point to pause this video and try this stuff. And v is cos t all squared. So this is going to give us 4 cos t for u prime. V prime is going to be a bigger mess. It's going to be 2 cos t times the derivative of cos t, which is negative sine t. Or v prime would be negative 2 sine t cos t. Okay. Which you might recognize from a double angle formula. I'm not sure that it makes your life a whole lot easier to use it at this point. Let's now find the acceleration function, which is v prime of t, and that's u prime by v plus u, 4 sine t, by v prime, which is negative 2 sine t cos t. Woo, there's a lot going on here. So acceleration would be 4 cos cubed of t plus, I guess that'll be plus a negative, so minus 8 sine squared t cos t. Okay. And hopefully we haven't made any goofs there. All we've done is use the product rule, but there was a fair bit going on. The next question says find acceleration, velocity, and speed when t equals 6. So in part C, we're going to find acceleration when it's 6, and that just means subbing in. So make sure that you're in radian mode, and we can find that it's 2.94, and that will be meters per second. Velocity is going to be negative 1.03 meters per second. And speed is the absolute value of velocity, or that would be 1.03 meters per second. Now, getting the correct acceleration depends on you doing part B correctly. I want to walk you through how you could do this if you just had the velocity function, or what's given to you. In our calculator, I'm going to put 4 sine x brackets. I'm going to open another set of brackets, and I'm going to put in cos x, close, and squared. That's what cos squared means. I'll make sure that I'm in radian mode, and I'll just go with basic window settings in the absence of knowing exactly what I want to figure out. And if I want the velocity when time is 6, I go second, trace, and I just choose value, the first thing. And I'll tell it the x value is 6, and it will tell me the velocity is negative 1.03. It's in blue there at the very bottom. If I want the speed, it's just the absolute value of that. If I want the acceleration, this is really sneaky. Acceleration is just the derivative of velocity. So I could go second, trace, go down here, and find the derivative. So then that's number 6. The derivative of this function at 6. And it will tell me 2.94 without having to do any other substitution. So a of 6 by substitution is 2.94, or by just looking at v prime at 6. D asks us at t equals 6 whether it's speeding up or slowing down. And what we need to do is compare these two values. At t equals 6, the particle is slowing down because velocity and acceleration have different signs. So velocity is negative, but positive acceleration means that it's increasing, so the actual bigness of the speed is getting smaller. Lastly, it asks us for the displacement, or the net displacement, over those first 6 seconds. So that would just be the integral of velocity from 0 to 6. And then it asks us for total distance. Okay, and recall that that is the definite integral of speed, or the definite integral of the absolute value of velocity. Both of these things are easy to put in your GDC, particularly if you have the function already in there. So I'm going to press second mode to quit. We could do this graphically, but I like to just do it by pressing math, go down to fn int, the definite integral. I go from 0 to 6 on y1, so I press alpha, trace, I choose y1, I dx. There we go. There's our net displacement. In the end, it didn't move much from where it started, or it didn't end up very far from where it started. How much it actually moved has to do with the total distance. So we'll do the same thing, definite integral from 0 to 6 of the absolute value of speed, so of velocity rather. So I press math over for number and get these absolute value signs. I press alpha, trace for y1, and I get 5.18. So net displacement is 0.153 meters, and distance traveled is 5.18 meters. And you can infer from that that it changed directions at least once in there. Since it's a trig function, it probably changed directions a few times. So that brings us to the end of this recap of kinematics in the context of trig functions. There are some practice questions on page 574, numbers 1 to 6. I hope this has been helpful. Good luck with the material, and take care, folks.